This is a required review for chapters 28 through 29, mostly for 28. We're going to do one of each kind of the chi-square test. So our first one says, the New York Times conducted a poll on women's issues. They asked people the question, do you get enough time for yourself? And the data can be summarized in the following two-way table. And it wants to say, are feelings of self-care and gender associated? So kind of, are they, when they say associated, sometimes the person that writes our exams likes to say associated when she means, do they affect each other? So when she says associate, she means, do they affect each other? Answer the following questions and then make your conclusion. Okay, so first of all, I look at this and I say, okay, we want to know, do they affect each other? So what test are you going to use? If we want to know if they affect each other, this is going to be a chi-square test of independence, because we know how to do two chi-square tests and they're pretty similar but just a little different. So it's useful to be able to tell which one's which. Also, when I look at it, I notice like, oh, look, there's men or women, and then each group of men or women can say yes or no. So it's kind of this cross classification table. And I know that it must be a chi-square test of independence, because a chi-square test for goodness of fit looks more like our next problem. Notice how it'll give you a lot of percentages and then just like one column of what you observed. So that's how you can kind of tell the difference. But most importantly, if it says, do they affect each other? Are they independent? Are they dependent? Are they associated? If it says anything like that, we're basically asking, do they affect each other? So we want to do a chi-square test of independence. When I look at this, this looks like the data. This must be the observed counts. And really, well, I was going to say before I read the rest of the problem, I should probably read it. But I know I'm going to want to do another table with my expected counts. So we'll kind of make the same table unless you have room to write on the first table. But if you're doing this on an online exam, you'd want to just write it on your own paper so you can work with it. Okay, so we know we have our observed counts. We want to find our expected counts. Let's read through the problem just to make sure we know everything we're supposed to do. So what are the hypotheses? Our null hypothesis is always that, let's see, gender and the answer are independent, meaning they do not affect each other. The alternative would be that gender and the answer are dependent. So the null always has to be if they're independent, they don't affect each other, kind of status quo. The alternative, what we're hoping to show, is probably that they do affect each other, that they're dependent, they affect each other, or depending on who writes the exam, occasionally she might say they are associated. Somehow they're affecting each other. She says associated like that. Part B, find the observed count for the women who say yes. So we're looking for women who say yes. Our observed count, the one we actually got, was 482. Now let's find the expected count for the women who say yes. So women who say yes, that would be this spot right here. So when we find expected counts, that's always going to be equal to our row total times our column total divided by our grand total. So our row total for women is 1,025 times our column total of 657 divided by our overall total of 1,497. So I get 449.8. You'll notice on the exam, she wants to make sure you know how to do all these intermediate steps. So we do not always do all these intermediate steps on the homework or on the reviews. But she will probably ask you some of these things. So she might ask, like, find the observed count or find the expected count. Okay. And it would be for just that one. That doesn't mean you don't have to do it for all of the values, but she's going to ask you about one specifically because grading an online exam, you can only ask specific parts. So we found our expected value, 449.8, for the women who say yes. Now we do need to find the rest of the expected count. She's just not going to ask you all of those just to save time, but you are going to have to do it to do the rest of the problem. So like if I want to find men who say yes, let's see what I need for men that say yes. I would have to do 472 times 657 divided by 1497. And that should give me 207.2. For men who say no, we'll do the same thing, but it'll be 472 times 840 divided by 1497. So we should get 264.8. And for women who say no, we should get 575. Now, you don't have to do this step, but I do like double checking my work. One way you can double check your work is add up the totals. Do your totals match what you had before? They should. So 207.2 plus 449.8 gives me 657. Hey, that matches, so we're doing good. Or 264.8 plus 575. Notice this one is a little bit more off just because of rounding. So 264.8 plus 575 gives me 839.8. That's close enough to 840. We count it. We don't worry about rounding. It's just we want to make sure that everything added up. And we get 472 and 1024.8. Again, close enough. We're just trying to make sure everything adds up. If I add this way, I get 1497. If I add this way, I get 1497. Give or take some rounding. That's just a nice way to double check before you do the rest of the problem. Now we know that our next step after we do observed counts and expected counts is we're going to have to find that chi-squared test statistic. When you find your chi-squared, so I'm going to skip down for a little bit, just write this down. So for part E, what is the test statistic? Chi-squared is always equal to our sum. We're going to have to do each observed count minus our expected count squared divided by our expected count. So that's how we find our test statistic. Now in the past, I've just kind of come down here and wrote each one out, but I saw someone do this with the table, or one of the other professors do it with the table, and I've never really done it that way. But it does make it a lot easier to organize our work, so I think I might start doing it. So we'll have one column for all of our observed, one column for all of our expected, and then we'll do our observed minus our expected squared over our expected. So notice our chi-squared says we have to do observed minus expected squared over our expected for every single cell and then add them all up. So instead of doing this in one step, I'll do it in a table to make sure I don't miss anything. So if I'm going to write down the observed, just make sure that you're very careful and everything lines up. So I'm going to go 175, 482. So I'm going to go down. I don't have to go this direction. I just have to make sure that everything matches up. So I'll do 175, then 482, then 297, then 543. Okay, for our expected then, make sure you match up the same cell. So 175 matches to 207.2. So usually I just do this what matches in my head and write it down here when I find my test statistic. But I do mess up quite often and match up the wrong things. So I think this table will just help us not mess up. So 482 matches 449.8. 297 matches the 264.8. And 543 matches 575. So let's find the observed minus expected squared over the expected for each one. So we're going to do 175 minus 207.2 squared divided by 207.2, which should give me about 5.0. And our next one will be 482 minus 449.8 squared divided by 449.8, which gives me 2.31. And 297 minus 264.8 squared divided by the expected. Make sure you divide by the expected, not the observed. So we get 264.8. That should give me 3.92. And if I do 543 minus 575 squared and divided by 575, I get 1.78. So again, for every set of cells, I did observed minus expected, squared divided by expected. And I have to do that for each of the cells. This table, while not required, just made it a little bit easier for me. So now, like if I come to part D, and part D says, find the chi-squared component for the cell of women that say yes. On the exam, it's hard for her to check to see if you know how to find all of these correctly. So she'll ask you to just find one. So the chi-squared component for women who say yes was this one, the 482 and 449. So that would be this one right here. For women, our chi-squared component means just the chi-squared part for that one cell was our 2.31. So you find your table, do it for everyone. The one for the women is 2.31. And what is our test statistic? If chi-squared was supposed to be the sum of everything that we found up above, well, now all we have to do is just add them up. So chi-squared is going equal, let's add everything up. 5 plus 2.31 plus 3.92 plus 1.78, which gives me 13.01, depending on how you round. It should be something close to that. What are the degrees of freedom? Now the problem is you have different degrees of freedom based on which test, and unfortunately I'm not the one that gets to choose what goes on your formula sheet, and you might have noticed there's nothing for degrees of freedom on your formula sheet for the exam, so you will have to memorize this. For chi-square test of independence, notice we have rows and columns. And you want to remember for this class, almost everything you've learned for degrees of freedom, well, everything you guys have learned for degrees of freedom is always something minus 1. So because we have rows and columns, for our chi-square test of independence, we'll do rows minus 1 times columns minus 1. Sorry, number of rows and number of columns. So in our case, how many rows? Remember, don't count your totals. We have 2 rows and 2 columns. So it'll be 2 minus 1 times 2 minus 1 for the columns, which gives you 1 times 1, or 1. Okay. What is the p-value? Well, this is a chi-square test, so we're going to use the chi-square table. And we want to find the area to the right, so we'll look in the right tail. So here's chi-squared equals 13.01. We want the area to the right. We have 1 degree of freedom. So look at 1 degree of freedom. You're looking for the number 13.01. It's going to be somewhere way off here, so our p-value is going to be something less than 1%. Probably quite a bit less than 1%. But we'll just say it is less than 1%. And our final part for this problem, what do you conclude? Well, I'd probably say something like, this is a small p-value, it's less than 1%. So it's less than the cutoff. They didn't tell me a cutoff, so we'll say a cutoff of 5%. So we will reject the null hypothesis. I'm going to say something like, we have evidence that gender affects the answer. So you could say affect, you could say associated, you could say dependent, you could say not independent. Any of those are all ways to say they're affecting each other. So dependent means they affect each other. Independent means they don't, so not independent means they affect each other. Associated means they're affecting each other somehow. So any of those words would work for your answer here. Part 2. A student believes that Mars M&Ms use an even 20% for all the colors but red and yellow. He believes that red and yellow are each 10%. He obtains 24 packs of plain M&Ms throughout stores in his county. He creates this table to test the hypothesis that his model is correct. So it didn't write it down for us, but notice how it's giving you percentages. When I'm given percentages, I realize it's probably going to be a chi-square test for goodness of fit. Because they're saying we know what our percentage, we think the percentages should be, and we want to see if the data supports those percentages. So the percentage that he thinks is supposed to be, he said 20% for everything but red and yellow. So red is 10%, yellow is 10%, and everything else should be 20%. So let's just add this to our table. You'll notice it told us our observed counts for each one, and then it gives us a spot to find our expected values, and it gives us a spot to find our chi-squared components. Let's look at our parts. Find the observed count for green M&Ms. Well, if I look at green, my observed count is just 86. That's what I actually got. Find the expected count. Well, it's supposed to be 20%. And then we'll times it by what? We'll times it by our total. So 20% for green times our total of 436. Now, how do you actually put that in your calculator? You'll do 20 divided by 100 because that's a percent, times 436. Equals 87.2. Okay, we found the expected count for the green M&Ms. Now, on this specific problem, you'll notice that on part D, she actually gives us our chi-squared value. So we don't necessarily have to be able to find all of these expected values. This is something to save you time. Okay. But I am going to write in what they are, in case you wanted to try them yourself, just to make sure you know how to do it. So like if I want to do red, I would do 10%. So I do 10 divided by 100 times by my grand total of 436. Should give me 43.6. So I'll fill in the rest here so you can double check your work if you need to. So I got these values, and just to double check, add them all up, you should get to something close to 436 because that was your old total. Your total should match. That's just a way to double check your work. Now let's find the chi-squared component for the orange M&Ms. Now again, because you are given your chi-squared test statistic, you don't have to find all of these, but she does want to make sure that you do know how to do it, so she'll ask you for one. So it says find the chi-squared part just for the orange cell. So remember, chi-squared is the sum of, and so we'll do each observed minus expected squared divided by expected. She did switch these columns, expected first, so make sure you put things in the right spot. So we need observed first. Our observed was 77. Our expected value was 87.2 squared divided by 87.2. This should give me 1.19. So that's the chi-squared part just for the orange M&Ms. So when we say chi-squared components, that's the observed minus expected squared divided by the expected. I'll fill in what all of these are just so you can double check your work if you wish to. So I found each of the chi-squared components so you can double check your work if you want to. Again, we didn't have to. She told us our chi-squared test statistic. This is just if you wanted to practice. So once you had all the chi-squared components, so if you were practicing, then chi-squared is just going to be the sum of everything you had right there. So if you add it all up, you get 9.854 is what I got. So that's how it was rounded to 9.86. So you just add up all of the chi-squared components. Okay. What are degrees of freedom? Notice this is a chi-square test for independence. You don't really have like rows of data and columns of data. You only have one column of data. It has a different degrees of freedom. It's number of categories minus 1. So in our case, we have 1, 2, 3, 4, 5, 6. 6 categories or 6 colors. So 6 minus 1 is 5. What is our p-value? Well, it's always going to be a right tail test because chi-square tests are always right tail tests. So look for the right tail. We have 5 degrees of freedom. Here's our chi-squared equals 9.86. let's see, 5 degrees of freedom. We're looking for 9.86, which should be about here. So it looks like we're between 5 and 10%. Let's see then. Would we reject or fail to reject the null? This is a big p-value, so we will fail to reject the null. And I just realized we were never actually asked for the null and alternative hypotheses. We should probably do that, since the hypotheses are the most important part. And otherwise, how would we know what we're rejecting? So sometimes she will ask you for the null and alternative hypotheses, sometimes she won't. Just to save time, she picks and chooses which parts to ask from which questions. So even if she doesn't ask you, you need to write down the hypotheses just so you know what you're doing in the problem. And if you forget and you get to the end, go back and write them in. So the null hypothesis for a chi-square test of goodness of fit is that the proposed percentages fit the data. The null is always that they fit. Status quo, they fit the data, nothing too exciting. Okay, and the alternative is that the proposed percentages do not fit the data. So the data doesn't seem to match the percentages we gave. In our case, it says he fails to reject it, which means that his percentages might actually fit it. But let's write it correctly. So when you fail to reject the null, you say something like, let's emphasize this, we did not find evidence that the percentages do not fit the data. Okay, I know that's double backwards. If you wanted to say it more in English, you could say something like, the model might actually fit the data. Again though, we always use our double negatives because it's always in terms of the alternative. So we did not find evidence that the percentages don't fit the data. That's my final answer, or my official answer. Just if you were explaining to your roommate, you might say, oh, well, the model might actually fit the data. We haven't shown that it does or anything, but we don't really have any reason to think that it doesn't. Now this last question is from chapter 29. It says, suppose this study was replicated with 50 other students and a majority of the students had statistically significant results at the 5% level. If the null hypothesis is true, about how many of the 50 students would have statistically significant results simply by chance? Okay, so let's do a little bit of background here. First of all, when we do a test at 5% cutoff, okay, that means, let's write this way, if the null is true, we will still get small p-values and reject the null 5% of the time. So now back to our problem saying if the null is true, okay, that's what we said. How many students would get a statistically significant result just by chance? So that's what we just said. So we expect small p-values or statistically significant results just by chance 5% of the time if the null is true. It's kind of like confidence intervals. When we do this, we have no idea at the end of the day whether or not our test gave us good results or not. We just hope that, oh, we know it'll give us good results like 95% of the time. Hopefully this is one of those 95% that gave us good results. So then if you have 50 students, so let's see, 5% of 50 students is, let's see, to do 5%, we'll do 5 divided by 100 and then times 50, so that'll be 5% of 50. Or 2.5. So if the null is true and 50 students take their own samples and do their own tests, then about 2.5 will get small p-values and reject the null.